Welcome to this lecture on one of the most dramatic moments in the history of physics, Rutherford scattering. Today we're going to explore how a few impossible observations completely overturned our understanding of atomic structure. Let's set the scene. It's 1909. The scientific community is quite confident about the structure of the atom. The dominant model at the time was J.J. Thomson's Plum pudding model. This model proposed that atoms were like a positive pudding with negative electrons scattered throughout, like plums in a pudding. Picture a sphere of positive charge with electrons embedded inside. The positive charge is spread out uniformly throughout the entire volume of the atom. Now here's the key. This model made very specific predictions about what should happen when you fire particles at atoms. Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden designed an elegant experiment. They fired positively charged alpha particles at an extremely thin gold foil, only a few atoms thick. They surrounded the foil with a detector screen coated with zinc sulfide, which would produce a tiny flash of light whenever an alpha particle hit it. Let's think carefully about what the Plum pudding model predicted. This is crucial for understanding why the results were so shocking. In the Plum pudding model, remember, the positive charge is diffuse, spread out over the entire atomic volume. This means that when a massive, fast-moving alpha particle encounters this diffuse positive charge, it should experience only very small deflections. The alpha particle might be deflected by a small angle, maybe a degree or two at most, as it passes through this diffuse positive charge. Now let's do some physics. Can we estimate what deflection angles the Plum pudding model predicts? The alpha particle has a charge of plus 2e. The positive charge in the atom is spread over a radius of about 10 to the negative 10 meters. The electrostatic force between charges is K times Q1 times Q2 divided by R squared. Here's the critical point. In the Plum pudding model, at any given instant, the alpha particle only interacts with a small fraction of the total positive charge nearby. The scattering angle theta is approximately K Q1 Q2 divided by m versus squared b, where b is the impact parameter, the distance of closest approach. When you plug in typical values for the mass and velocity of alpha particles, you find deflection angles of much less than 1 degree. We're talking about deflections of less than 0.01 radians, which is less than 1 degree. And here's the key prediction. Deflections larger than 90 degrees should be essentially impossible. The probability should be vanishingly small. So what actually happened when they performed the experiment? The results were absolutely astounding. As expected, the vast majority of alpha particles went straight through the gold foil with little or no deflection. But here's the bombshell. About 1 in 8,000 alpha particles bounce back at angles greater than 90 degrees. Some alpha particles were coming back almost in the direction they came from. This was completely unexpected. Rutherford later said, it was as if you fired a 15-inch artillery shell at tissue paper and it came back and hit you. Let's quantify just how impossible these large angle deflections were according to the Plum pudding model. Here's a question. According to the Plum pudding model, what's the probability that an alpha particle would be deflected by 90 degrees or more? In the Plum pudding model, to get a 90-degree deflection, you'd need many small deflections to add up coherently in the same direction. Statistical calculations show the probability is something like 10 to the negative 3,500. This is unimaginably small. To put this in perspective, this is far less likely than winning the lottery 100 consecutive times in a row. Yet experimentally, they observed it about 1 in 8,000 times. The discrepancy is absolutely enormous. What does this tell us? When your prediction is wrong by a factor of 10 to the 3,500, you don't just tweak your model. You throw it out completely. The Plum pudding model cannot explain these observations. It's not close. It's not even in the right ballpark. It's fundamentally incorrect. To deflect an alpha particle by 90 degrees or more, there must be something incredibly massive and highly concentrated in the atom. Rutherford realized that all the positive charge and most of the mass must be concentrated in a tiny region at the center of the atom. He proposed what we now call the nuclear model, a tiny, dense, positively charged nucleus surrounded by a cloud of electrons. The nucleus contains all the positive charge concentrated in a region about 10 to the negative 14 meters across. That's 10,000 times smaller than the atom itself. Now let's see how brilliantly the nuclear model explains all the observations. Most alpha particles miss the tiny nucleus completely. They pass through the mostly empty space of the atom, experiencing little or no deflection. This explains why most particles go straight through. The atom is mostly empty space. But occasionally, an alpha particle comes close to the nucleus. Now all the positive charge is concentrated in one tiny spot. The electrostatic repulsion is now enormous because the charges are very close together. This can produce deflections of any angle, including backscattering. Let's recalculate the probability of large angle deflections in the nuclear model. The probability is roughly the ratio of the nuclear cross-sectional area to the atomic cross-sectional area. That's R nucleus over R atom all squared. The nucleus is about 10 to the minus 14 meters. The atom is 10 to the minus 10 meters. So the probability is about 10 to the minus 8. 10 to the minus 8 means about 1 in 100 million. When you account for Gould's atomic number and the detailed scattering geometry, you get very close to the observed 1 in 8,000. Rutherford derived a precise mathematical formula that predicts the number of particles scattered at each angle. This is the famous Rutherford scattering formula. N of theta equals NINT over 4 R squared times K Z1 Z2E squared over 2K all squared times 1 over sine to the fourth of theta over 2. And here's the remarkable thing. This formula matches the experimental data perfectly across all angles from 0 to 180 degrees. The 1 over sine to the fourth of theta over 2 dependence is the signature of scattering from a point charge. This is direct evidence for the nuclear model. We can even use the scattering data to estimate the size of the nucleus. When an alpha particle is backscattered at 180 degrees, it must have approached the nucleus to some minimum distance. At the closest approach, all the kinetic energy converts to electrostatic potential energy. So d minimum equals kz1 z2e squared divided by the kinetic energy of the alpha particle. For typical alpha particles with kinetic energy around 5 mega electron volts scattering off Gould, this gives about 3 times 10 to the minus 14 meters. This tells us the Gould nucleus must be smaller than this distance. Modern measurements show it's about 7 times 10 to the minus 15 meters. Let me give you an analogy that captures the essence of this discovery. Imagine you're trying to map an invisible obstacle course by throwing balls through it in the dark. If the obstacles are big and soft, like hay bales, almost every ball will be deflected gently. This is like the Plum pudding model. But if the obstacles are tiny steel spheres, most balls will pass through untouched. But the rare ones that hit will bounce back dramatically. This is like the nuclear model. The key insight is that the rare, dramatic events, the outliers, tell you more about the true structure than all the common, gentle deflections combined. This discovery teaches us profound lessons about how science works. Lesson 1. Don't dismiss rare events as mere experimental error or noise. Sometimes the outliers are telling you something fundamental. Lesson 2. Quantitative predictions are crucial. Rutherford could say the Plum pudding model was wrong because he could calculate what it predicted and compare it to data. Lesson 3. Be willing to completely abandon even widely accepted models when the data clearly contradicts them. Lesson 4. Sometimes the simplest explanation for anomalous data is radical. The nuclear model was simpler than elaborate modifications to the Plum pudding model. Of course, Rutherford's nuclear model immediately raised new questions. Question 1. If electrons orbit the nucleus, why don't they radiate energy and spiral inward? Classical physics predicted the atom should collapse in a tiny fraction of a second. Answer. This puzzle helped motivate the development of quantum mechanics. Bohr showed that electrons occupy discrete energy levels and don't radiate when stationary states. Question 2. The nucleus contains many positively charged protons. The electrostatic repulsion should blow it apart. What holds it together? Answer. This led to the discovery of the strong nuclear force, which is much stronger than electromagnetism at very short distances and binds protons and neutrons together. Today we have an even more detailed picture of atomic structure. We know the nucleus contains protons and neutrons, which are themselves made of quarks held together by gluons. Electrons don't orbit in simple circles but occupy complex quantum mechanical orbitals described by wave functions. But Rutherford's fundamental insight remains perfectly valid. The atom consists of a tiny, dense, positively charged nucleus surrounded by a diffuse cloud of electrons. Let me summarize the key points of this lecture. First, the Plum pudding model made specific, testable, quantitative predictions about alpha particle scattering. Second, careful experiments revealed rare but impossible events, large angle deflections that were 10 to the 3,500 times more common than predicted. Third, these outliers couldn't be explained by tweaking the old model. They demanded a revolutionary new picture. Fourth, the nuclear model not only explained the outliers, but predicted the entire scattering distribution perfectly. Finally, this teaches us that rare events, when properly analyzed, can overturn even widely accepted theories and lead to profound new insights. This is one of the most beautiful examples of the scientific method in action. A few impossible observations, carefully analyzed, revealed the true structure of the atom and changed physics forever. Thank you for your attention.